Hi everyone, this is Snake here, and in today's video, we are going to take a deep dive into the world of the binary number system. Now, from the very get-go, I'm going to be clear with you. This video will not be like the other JEE or GATE exam videos that you watch on YouTube. No, this will give you a sneak peek of what happens under the hood, rather than you memorizing some process or algorithm to get the job done. So, the first question we need to ask is what is the number or what is the number system that we use? Okay, so in order to understand our number system and its philosophy, we must first see it in a contrasting image with a different number system. And the very different one is the Roman numeral system that you have learned in your childhood, basically. In the Roman number system, you see the numbers are represented by symbols, basically. 1 is represented as a straight line, 5 is V, 10, 50, 100, 500, 1000. You see, you already know the most obvious difference, that there are no zeros in their system, they didn't have it. But there are other observations that you can make to their system. You see, they had a particular preference for 5 and 10 and their multiples, basically. And also the point that every time they reached a particular checkpoint, let's say 50 or 100, they reduce the number down to a particular character, a particular symbol, basically. Now, what this means is that as the numbers grow bigger and bigger, let's say it becomes a 1 billion, they could just reduce it down to some particular character, basically some particular character, and the length of the number is small. Why did they choose to do this? You see, the Romans used to maintain records and data, and they realized that if the size of the number is smaller, they can efficiently store that data and also remember it and maintain it as well. It would be easier that way. Now, contrasting that to the modern number system that we use today, that there is a huge difference in philosophy here. You see, we have decided that we are going, rather than changing the symbol for as the numbers grew bigger, we restrict ourselves to a particular set of numbers. In our case, we restrict our values from 0 to 9. There are only 10 unique symbols to our system, and what we have decided is that as the numbers grow, they will have a weighted value associated with it. What it means is that in let's say a number like 1, 2, and 3, it has a weighted value associated based on the position of the digit, position of the number, basically. This is the units place, this is the tens place, this is the hundreds place. And what this means is that this number is achieved by 1 times 100 plus 2 times 10 plus 3 times 1, which will give us the number, basically. The disadvantage of such a system is that as the number continues to grow, it will start covering up the entire page, and very large number is very large. A very large number will cover a huge chunk of the page, basically. So now is the time for a creative inspiration. You see, earlier we restricted ourselves to only 10 symbols, 0 to 9, to make all the numbers. But what if we restrict ourselves to only 5 symbols, 0 to 4? What would that mean? What would that look like? So let's see. From number 0 to 4, 1, 2, 3, and 4, it would look just the same, 0, 1, 2, 3, and 4. But when it reaches 5, it would become 10. Why? Remember, expand it. 1 times 5 plus 0 times 1. What would that give? 5. Right? Similarly, 6 would be 11, 7 would be 12, 8 would be 13, 9 would be 14. And when it comes to 10, it will become 20. Why? Again, expand it. 2 times 5 plus 0 times 1. What does it mean? it becomes 10 basically. So what we did right now is that we worked in the base of 5. That is, we used a number system where there are only 5 unique different symbols. And likewise, you can choose any number of symbols to work with. You can choose a system where there are only 3 different numbers, 0, 1, and 2. Okay, like 0, 1, and 2. This would be a base of 3. You can choose 4, 0, 1, 2, and 3. There will be only 4 set of symbols, and it would all loop around like this. From when it reaches the value 4, it would become 10. And this is a very important observation here that you can make, is that any number any number will always be the number 10 in its own particular base. If you say you go to a system where there are 16 different symbols to represent numbers, then 16 in that number system will always be 10 in its own system. Basically, always remember this: any number in its own system, in its own base, will always be represented as the number 10. So understanding this, what if we choose a system where there are only two symbols, 0 and 1? What would that mean? Obviously, it means that now we can take a deep dive into the binary number system, where there are only two different symbols to represent the numbers. Now, as I said, the binary number system has two sets of symbols, 0 and 1. This is all we have to work with. Now, what does a binary number look like? Let's say 1101. And you see, there are only two different symbols that we have to work with, and with this we can represent any number we want to. And like any other system, this is a weighted system as well. This is the units place, the tens place, the hundreds place, and the thousands place. Okay, now, and like the weighted system, it is represented as 1 times 10 to the power of 3, but here 10 is in the base of 2, remember that. Then 1 times 10 to the power of 2 at the base of 2 as well, plus 0 times 10 to the power of 1 base of 2, plus 1 times 10 to the power of 0 at base 2. This is how its expanded representation looks like. But also, this is a good segue to the discussion of converting a binary number to a decimal number. You see, and the job is already half done basically. You see, all we just need to see that this representation is in base 2. We just need to go to base 10. So in base 10, it would simply be 1 times 2 to the power of 3 in base 10, plus 1 times 10, sorry, not 10, my mistake. It would be 2 to the power of 2 base of 2, plus 0 times 2 to the power of 1 base of 2, plus 1 times 2 to the power of 0 base of 2. See, and all we have to do is just calculate. This would be 8, 2 cube is 8, 1 times 8, plus 1 times 4, plus 0 times 2 would be 0, and then finally it would simply be a 1. 1 times 1, 1. Okay, now this would equate to 8 plus 4 plus 1. That would simply be 8 for 12, 13. It would be 13. This would be in base 10. So we went from 1101, which is in base 2, to 13 in base of 10. We finally did our first binary to decimal conversion, guys. Okay, just now we saw the conversion of a binary number to a decimal number. But now let's tackle the reverse situation. Let's convert a decimal number to its equivalent binary number. Okay, uh, let's choose a random number, say 52. Okay, 53 is a good odd number. It is in the base of 10. Okay, now the process, the algorithm to find the binary equivalent is simply this. You take the number 53, okay, and then you divide it by 2. You get the quotient to be 26 and the remainder to be 1. You note down the remainder on the side basically. Then you do the same again for 26. It would leave a remainder of 0 and the quotient of 13, and you repeat the process continuously. This will leave a remainder of 1. This will leave a remainder of 0. 3 would leave a remainder of 1 and a quotient of 1 as well. And finally, you do the final step where you divide 1 and you get the quotient of 0 at the end. And to get the binary equivalent of it, you read it in the reverse direction. You read the remainders in the reverse direction. And it would give out to be 110101. So 53 is this number in its binary equivalent basically. So most teachers would basically just stop here and tell you this is how it is done. But let's not be satisfied right now. Let's see why this actually works, why this process gives us the binary equivalent. To do that, let's start at the source of division. We all know that dividend is divisor times quotient plus remainder. So let's compare it with the steps and see what we are doing here. At first, we are taking the number and we are basically converting it into dq0 plus r0, and then in the next step we are taking q0 and then we are converting it into dq1 plus r1, and then in the third step we are taking q1 and we are converting it into dq2 plus r2, and it goes on as long as till it reaches 0 basically. Now what we are going to do is we are going to back substitute things. Okay, so if we put the q1 value for this in this equation, what do we get? We would simply get uh, q0 is equals to d times dq2 plus r2 plus r1, which would basically give us d square q2 plus dr2 plus r1, and then we are going to substitute this value for q0 in the original equation, where d is equals to d times d square q2 plus dr2 plus r1 plus r0 basically, and then we are going to multiply this. So we will get d cubed q2 plus d square r2 plus dr1 plus r0. Now we have looked into 3 steps, that is why it is this equation, but it can go on any number of steps. So we'll convert this into a more general form, and the general form would basically look like this: d to the power n times q n minus 1 plus d to the power n minus 1 r n minus 1 plus d to the power n minus 2 r n minus 2 plus dot 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 plus d to the power 0 r0. Okay, this is the most general form of the equation that we'll achieve. Now I'm going to erase this upper part here. Okay, so now we will see something miraculous happen right now. Okay, now see that in the final step we get this quotient to be 0. and this is the final question that remains, the last question basically. So we can substitute this value to be 0. So what is the final equation that we will reach? We will basically see that it will attain the value d to the power n minus 1 r n minus 1 plus d to the power n minus 2 r n minus 2 plus dot 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 d to the power 0 r to the power 0. Okay, now here you see this is r0 r1 down to rn minus 1 basically. So you see what we are seeing here is that if we substitute this value for 2, isn't this just basically the binary expansion form where each individual digit is r, the r value basically, and that is multiplied to 2 to the power n minus 1 plus r n minus 2 times 2 to the power n minus 2 plus dot 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 2 to the power 0 times r0. And see that these values are in the reverse direction to the weight of the particular place in the digit. That is why reading this in the reverse direction gives us the binary equivalent. It's because of this. This is the proof to why this process actually works. See, my friends? Okay, now let's consider fractions. Okay, let's take a fractional number, say 0.625, a simple number, and it is in the base of 10, and we are going to convert it into its binary equivalent. Okay, the process to do this is simply multiply this number with 2. 0.625 times 2, which would give us basically 1.25. Now we take the integer part of it, and that is the answer, the output, and we take the fractional part and we repeat the step. So 0.25 times 2, that would give us 0.50. The output here is 1. And same here, the 0 goes to the output, and the fractional part, we repeat the steps again. Okay, so 0.50 times 2, that would give us 1.00. The output would be 1, and we take the fractional part. So finally 0.00 times 2 gives us 0.00, where the output is 0 basically. Now we continue the steps till we reach 0 or to the number of digits we want after the decimal point. And in this case the binary value is read top to bottom basically. So the binary equivalent of 0.625 is basically 0.101. 101. Ta-da! This is the binary equivalent of it. So let's get proving again. Here we are going to start off with the observation that this is a fraction. Okay, so we take the value to be sum p0 by q0. Okay, as a normal fraction is represented. In the first step, what we are doing is we are multiplying p0 by q0 with d. Here we are multiplying it by 2. We are multiplying a more general form. We are multiplying it with d. It would give us an integer part plus another fraction p1 q1, and in the next step we take this fraction part and again multiply it with d. So p1 by q1 times d will give us x2 plus p2 by q2. Okay, now what we are going to do is solve this equation by taking the d to the other side. So p1 by q1 now becomes x2 by d plus p2 by d q2. Okay, this much is clear, I guess. And then we basically substitute this value in the q0, this equation. Okay, which now becomes P0 by Q0 times D equals to x1 plus x2 by D plus P2 by dq2. Okay, and now again we are going to place this change the side of this d to this side, and the final equation would become p0 by q0, which is basically the d, the initial number. It turns out to be x1 by d plus x2 by d square plus p2 by d square q2. Okay, now a more general form of this equation would basically look like uh, x1 d to the power 1 plus x2 by d to the power 2 plus dot 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 xn by d to the power n plus the final fractional part, that would be pn by d to the power n qa. Now generally this part either becomes 0 or you stop till this point, which I said, that you want as many fractional as many digits after the decimal point as you want basically. So considering this, the final equation that we reach, I'll write it above here by erasing this. We get that d is equals to x1 by d1 d to the power 1 plus x2 by d to the power 2 plus dot 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 xn plus d to the power n. Now, isn't this the general form of an expanded form for the decimal number system? I mean, for the fractional parts of the system. Like if we replace this with 2, it would simply be x1 to the power of 2 to the power minus 1 plus x2 2 to the power minus 2 and so on plus xn 2 to the power minus n basically. And this is basically the expanded form of the fraction parts of any number. So this is why we, and you see this x1 is basically the first integer part, x2 is the second integer part and third, and the associated base values, weighted base values is as follows. So this is why the reason that you read these values from top to bottom, and it gives us a binary equivalent of a fractional number basically. The main reason for using d in all of these scenarios is to show that you can replace that with any number. It doesn't have to be specifically 2. Let's say if I replace 2 with 3 here and do this process, it would simply spit out the base 3 equivalent number for this particular fraction. And this applies to all the other processes that I have shown you before as well. So you see, it's a more generalized approach, and you can convert between bases of your own choice. That is always up to you. And with this I end my video. Please like and share my video and subscribe to my channel. And the final thing I want to say: to learn, never memorize. So bye everyone.